Welcome to this explainer. Usually when we think of geometry, we immediately picture this highly visual world, right? We think of shapes, angles, and physical space. But what if you could write down the exact DNA of those shapes using just numbers and letters? Well, today we're going to do exactly that. We're going to translate the visual world of geometry into the logical, highly structured language of algebra, and we'll be focusing specifically on the simplest, yet arguably the most vital geometric figure, the straight line.
Okay, let's take a quick look at our roadmap for today. We'll start where algebra meets geometry, do a quick recap of the basics, dive into the slope of a line, build some line equations, and finally, wrap up with distances and relationships. Let's get right into it. All right, Section 1, Algebra meets Geometry. Let's look at the philosophical roots of all this.
So, the mathematician H. Freudenthal once noted that geometry, as a logical system, is a means to make children feel the strength of the human spirit. I just love that quote. It reminds us that understanding geometry isn't just about, rote memorization or endlessly moving numbers around on a page. It's literally about unlocking the structural logic of the human mind. It's about feeling the strength of our own reasoning.
And to tap into that structural logic, we rely on a very specific field of mathematics. This revolutionary combination is known as analytical geometry. Think of analytical geometry as this brilliant translation guide. It lets us systematically study visual space using the precise, hard rules of mathematical analysis and algebra. Basically, it completely bridges the gap between what we physically see and what we can actually calculate.
And honestly, we have this celebrated French philosopher and mathematician René Descartes to thank for this whole shebang. Way back in 1637, his work, La Géométrie, first gave us the exact toolkit to give curves and lines a formal mathematical identity. I mean, before Descartes, algebra and geometry were basically living in two completely separate worlds. By introducing the notion of an equation for a curve, he forever changed how we understand the space around us.
Moving right along to Section 2, recapping the basics. Let's look at coordinate geometry.
Now, you might remember these legacy formulas because they literally form the grid that maps our physical and digital worlds. Just as a quick refresher, you use the distance formula to find the absolute space between any two specific points. Then there's the section formula, which you use for calculating internal divisions along a given ratio. The midpoint formula does exactly what it says. It allows you to find the exact, undeniable center of a line segment. And the area formula calculates the exact space contained within three coordinate vertices. These are your foundational tools.
To really ground this in reality, let's pull a concrete example right out of the chapter we're explaining today. If you apply that distance formula to the coordinates 6, -4, and 3, 0, the math spits out a perfect result of exactly 5 units of physical space. No guesswork, it's pure, predictable logic translating physical space right onto the coordinate plane.
Which brings us to Section 3, the slope of a line. Let's talk about its directional DNA. So, the absolute most important characteristic of a straight line is what we call the slope. You can really think of the slope as the line's directional DNA. It dictates exactly how that line behaves as it shoots across the coordinate plane. Algebraically, we represent it with the letter m. It's calculated as the tangent of the angle the line makes with the positive x-axis, or, a bit more practically for us, it's simply the ratio of the change in the y-coordinates to the change in the x-coordinates between any 2 points on that line.
And what's so cool here is how this elegant logic defines exactly how lines interact with one another. Take a look at this. Parallel lines, the ones that will never, ever touch no matter how far they extend, they share identical slopes, so m1 equals m2. On the flip side, perpendicular lines, the ones that smash into each other at a perfect 90-degree angle, their slopes will always multiply to exactly -1. So literally, just by knowing the slope, you instantly know how two lines behave around each other in space.
All right, Section 4, building line equations. Let's give these lines a unique identity.
Once you know a line's starting point and its slope, these formulas basically act as your ultimate translation cheat sheet. They let you build a line's exact identity based on whatever clues you're given. Like, if you just have a single point in a slope, boom, you use the point-slope form. Do you know where it crosses the y-axis? Then the slope-intercept form is your best friend. Know where it crosses both axes? You jump straight to the intercept form. It's this incredible flexibility that makes analytical geometry such a game-changer for mapping coordinates.
But here is the really wild part. Despite all these different specific forms we just looked at, every single straight line can ultimately be boiled down into one super elegant formula, the general linear equation. ax plus by plus c equals 0. As long as a and b aren't both 0 at the exact same time, this one equation can represent literally any line in the universe. It's the ultimate unified language of straight lines.
Finally, we arrive at Section 5, Distances and Relationships. Let's place some points in open space.
Okay, imagine you're standing at a specific point on a map, and you need to get to a straight road as fast as humanly possible. To find that absolute shortest path, the perpendicular distance from your specific coordinate point to the line, you just plug the lines a, b, and c values, along with your points x1 and y1 coordinates, right into this formula. And just like that, it flawlessly translates a physical, real-world distance into pure calculated algebra. Now, what if you want to know the precise gap between two parallel lines? Think of two train tracks running perfectly alongside each other. Because they're parallel, their a and b values in that general equation are going to be exactly the same. The only mathematical difference between them lies solely in their constant values, c1 and c2. So, finding the physical distance between them is as simple as mathematically comparing those two constants using this formula right here. It takes a messy spatial problem and turns it into simple arithmetic.
As we wrap up this explainer, it really leaves us with a fascinating thought. We've just seen how Descartes' brilliant logic gives us such total mathematical mastery over straight lines, right? We can map them, measure them, and predict their relationships with absolute perfection. But our world isn't just straight lines. It's full of waves, spirals, and parabolas. So if the simple mathematical translation of a straight line can perfectly map geometric space, imagine the immense power this analytical geometry holds for understanding the rest of the universe. How might these equations serve as the building blocks for the complex, unpredictable curves we experience every day? Keep that in the back of your mind as you continue your mathematical journey. Thanks so much for learning with me today.